לא, יש את העניין הזה, שכאילו קורקינט, אפשר אותך, אתה יכול להעלות אותו.
לא, ברור, לא צריך תשובה, רגע. אני אשלח את זה.
אופניים מתקבלים, יש רגולציה, אני לא שומע לדוגמה, אבל כאילו, יש כיוון...
זהו, שאני חיפשתי לחוקר של...
כאילו, אופניים רגילות,
שנייה האחרונה.
אבל עכשיו גם...
אתמול התחילה...
אבל הם אמרו שהם לא רשום.
אבל באנשים
זה נושא שנראה לי חבל.
לא, אפילו אולי שאל אותם, אמר לא, אמרנו שזה לא יודע.
כן.
יכול להיות שזה יקרה. לדעתי זה לא יקרה. זה לא יקרה.
Because we are early. Everyone is used that we are 10 minutes.
They're resynchronized.
Yeah, everyone knows you.
So there's supposed to be a bus coming from Weizmann.
Bus.
Bus.
To connect on the computer. Well, there's someone from Weizmann here already. Hi, מה נשמע? טוב. היי, ברח מצחר?
כל אחד לבד.
She didn't come in a bus.
No. They said they came on their own. היי, שלום.
חגי, אני מצטער שלא זה, לא יכולתי לבוא.
כן, אבל אני לימדתי אותו רק שם שלך.
אז אני אקבע איתכם יום אחר. לא, הייתי
מה? שחר. עכשיו קרן,
כי הרגשתי שאתם לא צריכים אותי.
ישבתי כבר יום תחזרו על חבר נדב. I'll be your king. You're already... You're already leaving.
Tomorrow, I leave it for the airport 3 a.m. Saturday. My Shabbat will start 4 hours early. Are you coming to dinner?
No, my wife.
You have
4. I have a girl. Skin. Just boys.
Ow!
It's bad. Your voice is really mixing up. So you think your VGA that one?
When I close the email,
צריך לראות שהלאות התחילה להקליק על אוטומטי. לחצתם את המסך? לחצתם? עוד לחצתם? אני לא רואה, אני לא לחצתי. כן, אני רוצה. מוזמן ללחוץ שוב. זה לא עובד. זה לא עובד? העליון לדעתי, הנה הוא נידק, הוא נידק עכשיו. אני רואה נידק. אז מה, זה ספייר? זה בשביל סטריאו. גם בשביל בכיתה הזאת, לא תמיד. זה לא אדירה לי. זה לא אדירה. There it is. Just works. Unbelievable. Without a weird color. Okay. Welcome to the last meeting of this course. Don't come next week. We won't be here. We cannot meet here on Sunday, but without the professor. If you want to
sometimes it loses it, and I open PowerPoint and say, find, open a recent file, and
This means you saved it in something random.
something random place.
There's Thursday the 16th.
Yeah, but
there.
there's nothing in the folder.
That's not good.
There was something in the folder last night. It must be a nerd.
20 icons. Maybe you stored it in the wrong folder?
Well, that's what I'm thinking. It would have the same name.
Search, what's the date today? 16th?
16th?
Yeah, look for 16th maybe.
Ah, there's, ah,
Maybe it's the right file, just misnamed it.
maybe I just.
Open up your PowerPoint, look at the most
Oh,
recent
yeah,
thing.
open recent file.
Yeah, that'll probably do it.
I never renamed the file. Yeah, it's stinky. That looks good. Spinning wheel of death.
There you go.
That's the right one. I just said the wrong name. So much for the bus from Weizmann, right? I think.
These guys.
It's a minibus.
Mini. Very mini.
That's empty.
So I hear your name means seagull.
Yep.
So you're now seagull. Better than long hair guy?
Steven.
Could be a long hair seagull.
The long haired seagull. All right. So over the past 2 weeks, seems like infinity, we've covered all sorts of sensors.
This is a recapitulation, yes?
Yeah, exactly. And so today, well, it was supposed to be a recapitulation for Weizmann, but I decided to make, since the Weizmann people hadn't shown to any of the talks, they will know it's not a recapitulation, and I can talk about something different. So, in the US, we have something called the National Quantum Initiative. So how did this start? It all started when the Chinese hacked Padai Eisenberg's cell phone. And back in 2016, the Chinese launched a satellite called Mozi.
Mixius.
That's the English. In Chinese, it's Mozi. Named after the famous Chinese philosopher Mozi, okay, who invented the pinhole camera. This is the interesting story about Mozi.
It was invented in Europe, they used it.
No, this was several thousand years earlier,
Okay.
several hundred years earlier. So the pinhole camera was invented by Mozi, and it's widely believed to be the father of optics in China. So in 2016, they launched the satellite, also called Mozi, that is called the Chinese quantum satellite. So if you Google Chinese quantum satellite, you'll find everything about this. And on the satellite, they had 3 experiments. One was to do quantum cryptography, and one was to do teleportation, and the other one was to distribute entanglement. So I'm going to talk about all of those today in the first hour, and then I'm going to show how you make them into a network of sensors into the second hour. And so the satellite was launched in August of 2016, and I was told by my government it was a propaganda hoax and it would blow up on the launch pad. Not to worry. And I said, no, I think it's going to work. And then in 2017, they began taking data, and then everybody in my government completely freaked out because it didn't blow up. It did exactly what I said it would do. So you all have a copy of my book. It's in the folders for the students, right? The very first page is Schrodinger's Killer App, Race to Build the Quantum Computer. And you can find a paragraph where I talk about this satellite, and it says, the future quantum internet will have made in China stamped on it. And nobody believed me in 2013. But now they do. And so the satellite worked, and the Americans then responded as they usually do. They went from thinking it won't work to going crazy and throwing money at the wall and typical things we do in America. So now we have this new National Quantum Initiative. So I like to call this the Quantum Sputnik moment, right? Back in 1958. Back in 1958, everybody thought, well, Americans thought we're at least 10 years ahead of the Soviets, and then the Soviets launched Sputnik, okay? And all Sputnik did was, it was basically a nuclear warhead. Well, they took out the nuclear warhead and they put in a radio. They just circled the Earth and beeped. That's all it did. Beep, 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 beep. And once again, the Americans went crazy and invested a huge amount of money into the space program. And so now we're seeing this in the United States, huge amount of money into quantum technology.
Do you know what Sputnik means?
I don't know.
Companion.
Companion. Was this for the reporter?
Yeah, because I'm not coming to take good pictures of you for now.
The reporter came this morning to interview me at the 9:30, and Haggai Eisenberg spoke for the first 30 minutes in my interview, but even 30. And then luckily he had a meeting at 10 and had to leave, and the reporter locked the door and said, now we can talk. And so I'm actually telling you what I told the reporter this morning. What is it's an online news service, what is it called?
Wineland.
Ynet.
Why?
So I will be...
Why do you need a network of quantum sensors?
I don't know why, when you tell me.
Why do you need a network of quantum
But
sensors?
anyway, Ynet interviewed me and I'm telling you the whole story. So now we have this multi-million, almost $1 billion initiative to develop quantum sensors, quantum computing, quantum cryptography. And there's $1 billion just in the civilian budget. So I have to tell Tomer.
More than $1 billion.
More than So more than $1 billion in the civilian budget, but you don't know how much is in the Department of Defense budget.
How much?
Okay, so Tomer, you listening? Taking notes? What are you doing?
Actually,
Texting your wife. So I'm going to tell a funny story. You have to pay attention. This is a military story. So I'm in an Air Force base in Bossier City, Louisiana, where they have Air Force Nuclear Strike Command. So these are the guys in charge of launching the nuclear missiles. Okay? And so they're interested in upgrading their systems with quantum technology. So I organize a workshop and we have scientists, but half the people are in uniform like you. Okay? Wondering what is all this about. And there's a 3-star general. Normally they only let me talk to 2 or below, but it's 3 stars. And I'm sitting next to him, okay? Bad move. And then he has 2 assistants sitting next to them. And we're talking about quantum cryptography, which is not something I mentioned, but this is a way to use photons to secure data, unbreakable means. And China is doing quantum cryptography across their country. So the nice thing about quantum cryptography, it's unbreakable by a quantum computer. So people are worried Chinese or Americans will build a quantum computer and read all your data. But quantum cryptography in principle is unbreakable because it uses something called one-time pad crypto system, where if you have a set of random numbers here and another random numbers here, and you can then transmit perfectly secure information. The problem is I have to get the random numbers, the one-time pad, from Alice to Bob's without anybody making a copy. And in classical mechanics, somebody can always make a copy and then have a copy of the key and then read everything. So this is bad. But in quantum mechanics, due to the no cloning theorem, which you heard about today, you cannot copy a quantum state. So there's no way you can make a pad. Okay. So we're discussing this, and I read in Wikipedia that in America, only 3 agencies use the one-time pad because of this copying business. The CIA, the diplomatic corps, the embassies, and the nuclear launch codes. Okay? So I say to the general, as you know, the one-time I'm describing quantum cryptography, and I said, as you know, one-time pad is used to secure the nuclear launch codes. So he's in charge of the nuclear launch codes, so he should know. So he whispers to his assistant next to him, goes, is this classified? And then I said, it's on Wikipedia. Oh, okay, fine. And then, yeah, okay, we use the one-time pad. Great. And I go, well, there's a problem. You have to distribute the pad, right? Secretly. How do you get the pad around? He goes, well, we got a guy in a pickup truck named Buck. And he has a suitcase with 3.5-inch floppies. And on the I'm not kidding. And on the 3.5-inch floppies are the pads. And he drives around and hands them out to each missile silo where the nuclear weapon is. And no one is laughing. Everyone in the room is now quite afraid because the future of the Earth depends on Buck in a truck with 3.5-inch floppies. So I asked the one obvious thing, 3.5-inch floppies? And he's from Arkansas, so he has an accent. He goes, well, Professor, they don't make the 8-inch floppies no more. So that is what is the only thing keeping us from nuclear annihilation is Buck in a truck. And I said somebody
Like
could...
something from Dr. Seuss.
Yeah, I know. Okay. So I said, but he says, well, it ain't hooked to the internet, so you can't hack it. And I said, yeah, but somebody could bribe Buck or drug Buck and make a copy of the pads while he's in the bathroom or anything, and it's all over. And I said, quantum cryptography will allow you to send the pad securely. And then one of his assistants, he had 2 guys, they were docs. So I go, no, do I get to be a doc because they have doctors? He goes, well, you're the prof. So he asked one of the docs, what do you think? He goes to me, how much do you think it would cost to roll this out? And I said, $1 billion a year to start. And no one laughed. And he writes down, okay, reasonable number. And I don't. So I felt like the guy from the what's the TV show Austin Powers, where the mad scientist says $1 billion a year in the wrong time frame, and everybody laughs at him. Okay, so I've never said such a number in my life, but I thought anything lower than $1 billion, they won't take me seriously. Okay, so that's just to secure the nuclear launch codes is $1 billion a year. You ask what is the military budget? That's just one thing. Okay, well, that's a good story.
Just a side note.
Simba.
Most of the systems that
I'm holding Simba up to be blessed.
the circle of light.
Yeah, okay.
Anyways, most of the systems that are used for QKD are not really using a one-time pad. Even the ones you can buy commercially.
Okay.
And nobody, like I talked to one of the people who actually runs a company or started a company that sells it, and they can't tell you if it's how insecure that is. They don't know.
Okay. But so first of all, I was told when addressing the general who has no technical background, I should use hand puppets. Okay, so I don't think he even knew exactly what one-time pad was, but he certainly doesn't know these details. But that's the promise of quantum cryptography. I'm not selling a real thing yet. It gets bright. Okay, so and the idea then I had my high school student, Eliza, not Elisha. I said, well, we're going to model how to distribute the nuclear launch codes over a quantum network. And she goes, I go, that's your high school summer research project, okay? So she has this poster, and at the top, there's a network of fibers running with different nodes, and at the bottom there are 64 generals with buttons, okay? And at the top is Trump. And we call it the Trump Tower, and then she wanted to submit this for her science fair project, and the teacher said, can't we change it to something non-political? And so it became Emperor Nero wants to light Rome on fire, and he has 64 guys with torches, and he has to send the message. Anyway, this is what my high school students are doing, securing the American nuclear launch codes. All right, so networks of quantum sensors. Okay, blah, 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 blah. Somebody already sent in their report, thank you. All right, so this is all taken from my new book. The last one was Quantum Computing, Schrodinger's Killer App. The new one, I just submitted the book for the publisher January 1st, and then I got on the plane on January 2nd, flew to Israel. Okay, so it's now in the hands of the publisher. So this is from some chapters of this. It's not ready for prime time, but just keep this pre-ordered on Amazon now and get your copy. And also, if you bring me this book or the old book, paper, I can sign it. And then you can sell it. What is eBay in Israel? eBay. eBay. Okay, you can sell it on eBay. And then people will buy a book signed by, first edition signed by author, in case I'm as famous as Einstein or Maxwell, and then they will buy it for double what you paid, okay? So then, using that money, you buy 2 books, I signed both, okay? After a few weeks, we're billionaires, and we can retire to Malibu. Okay, so in the introduction to my new book, there's a guy who writes a comic strip called Saturday Morning Breakfast Cereal. The young people might know this. It's Zach Wienersmith. You know this one. Yeah. The young people love this cartoon. I love this cartoon. So this was a cartoon he wrote based on my previous book, where I made fun of your friend Penrose about quantum consciousness and all of that crap.
Dick's friend.
Yeah. Okay. So it's science journalism, not science, right? So this is the how to communicate physics. So this is actually in the beginning of my new book. Quantum mechanics, the entire field of quantum mechanics is about how you don't know what's in a box until you open it. That's quantum mechanics. And especially you don't know what's going on if there's a cat in the box. And you don't know anything. Relativity. Einstein invented this, suggests that one guy might say, it's like this, but another guy says, you buddy, it's like this. That's relativity. Okay. Einstein discovered that when an apple fell on his head, he gets the wrong one, and thought maybe it was me who fell on the apple's head. Okay, so this is the guy explaining to the newspaper, the students who will write, the guy who interviewed me today. This is what he's going to write. Okay. Finally, quantum computing is when you take a computer and put it in the box instead of the cat, and you open it later, and it solved an infinitely complicated problem. And that's because you don't know what's in the box until you open it. So this is all complete nonsense description of what's going on. Okay. But now to Professor Eisenberg's work. Could some of those things be mushed together to explain human consciousness? Absolutely! We will do an experiment. So there's a crazy guy named Penrose who thinks that the brain is
Roger Penrose, you know about
yeah, he thinks your brain is a quantum computer. So you make more money buying copies of my book. Okay, so there's a paper that came out in 2003 called Quantum Technology, the Second Quantum Revolution. And it's in your folder, okay, and I am the first author. So I was at a conference a couple of years ago in Hong Kong, and David Ashlam, you must know David Ashlam.
We were talking about him the other day.
So he quotes from the book, this. Second quantum revolution, the first quantum revolution gave us new rules that govern physical reality. Second quantum revolution will take these rules and develop them into new technologies. And he cites Milburn, who's the second author. And I raised my hand and I go, actually, I wrote this. He goes, who are you? So that's Ashlam. Okay. I was not famous enough to even register. And guess who drew this? What group produced this fancy picture? I have permission. This was produced by the artist of USTC John Wei Pan in China. Okay, so this is showing entanglement.
Of course.
Okay, so people go, what is quantum technology? And people have different answers for that. Since I invented the term, I get to define it however I like. So, and we've seen a number of these things, right? Quantum uncertainty, you measure the photon wave function, it collapses to horizontal or vertical randomly, you don't know which. On reality, I don't know if it's a horizontal photon or a superposition of a plus and minus 45 degree photon. I don't know if the cat is dead or alive or a superposition of dead and alive. It's unreal until you make a measurement. And then the last one, we saw this briefly with the Noon states, quantum non-locality. Entanglement means that if I make a measurement here, it can influence the outcome of a measurement made light years away. That's entanglement. Okay, so how do you make entangled photons? We're going to talk about entangled photons in the horizontal and vertical polarization. I didn't go too much into this. I had some Noon states in horizontal and vertical polarization. But this is a simple entangled state. So this is the original experiments for these kinds of states were done in the Tomer, are you talking during class again? Yeah, it's his fault. Okay. So you have a cesium atom in a gas cloud and it emits a pair of photons. But because of quantum unreality, you don't know if the horizontal one goes to the left, let me make sure I get this right, and the vertical one goes to the right, or if the vertical one goes to the left and the horizontal goes to the right. So classically, it would be either this or this, but quantum mechanically, it's a superposition, and you add them together. Professor Howell's falling asleep. He's thinking deep thoughts. Okay. So the first experiments, they actually had a cesium atom in a chamber. The table was 10 meters long. They had detectors here and detectors here. And the interesting thing is that you make measurements of the angles of the photons emitted in this process. You can measure horizontal, vertical, plus, minus 45 degrees, crazy angles like 22.5 degrees. And you plug you measure correlations between Alice and Bob. Alice is there, Bob is there. And you measure correlations between, you make measurements, joint measurements of the photon detections, plug them, look at the correlations, the second order correlation, plug them into a formula, and the formula spits out a number. It's called Bell's inequality. If the number is 2 or less, then classical mechanics or some variant of classical mechanics is right, and you have locality, which is what Einstein wanted. No spooky, spookheftige Werkverbindung, which in English is spooky action at a distance. Okay, so Einstein had a sort of competing theory to quantum mechanics called invariable theory that said, okay, we can get rid of all this unreality, uncertainty, and spooky action at a distance by replacing quantum mechanics with something like StatMech, where all of these correlations are just classical probabilities. And people argued about this from the 1930s until the 1960s. And then in the 1960s, Bell said, I have a test. You do this experiment, plug the numbers in. If you get bigger than 2, quantum mechanics is right and Einstein is wrong. If you get 2 or less, Einstein is right and quantum mechanics is wrong. So we, instead of arguing, go to the lab and test. So that's what they did, and the first experiments came out in the 70s using this gas cloud. What was the count rate? Maybe a couple of photons per second. So it took days and days and weeks to accumulate the statistics. So there was an experiment by Pipkin that ruled quantum mechanics out, but very low signal to noise. And then there was a follow-up experiment by a guy at Texas A&M University, Ed Fry, and he ruled quantum mechanics in and Einstein is wrong, but also at very low statistics. And then John Clauser, who was a postdoc at Berkeley, did an experiment with the same setup. And Clauser was convinced that he was going to win the Nobel Prize for proving quantum mechanics is wrong and Einstein is right. So he kept measuring the data and the data and the data. So here's 2, and here's 2 times the square root of 2. If you're in here, quantum mechanics is right and Einstein is wrong. If you're in here, the reverse. So the initial experiments, this is t as a function of years, right, are all clustered around here, so it's hard to tell. But Clauser, his experiments seem to show that quantum mechanics is right, which means he doesn't get the Nobel Prize. So he kept taking more and more and more data because he wanted to win the Nobel Prize. And unfortunately, his data started doing this until he had to conclude quantum mechanics was right and he was not going to win the Nobel Prize. He might win the Nobel Prize for this experiment. Okay, so, and then Clauser was unable to get a real job, a tenured professorship anywhere, so he went to go work for a government laboratory. And they took all of his equipment at Berkeley and they put it in the attic, stored it in the attic. Then this French guy with an outrageous mustache by the name of Alain Aspect, who has a very thick French accent, which John, what are you doing with these experiments? Okay, so he's a very nice guy. Anyway, not so nice. He calls up, he says, he's talking to John Bell, and Bell says, well, there are these experiments, but you really should be changing the beam splitters and detectors while the photons are in flight to rule another loophole out. And so Aspect calls up the physics department chair and said, whatever happened to Clauser's old experiment? He goes, it's in the attic, taking up room. You want it? Pay for shipping, you can have it. So this is a true story. They shipped Clauser's experiment
Without asking him.
without asking him, and he redid the experiment of Clauser, doing some changing the polarization settings while the photons were in flight, but mostly he had a good public relations team, and it made all the newspapers, everything, and the paper doesn't even cite Clauser's experiment, in spite of the fact he used Clauser's equipment and knew very well that Clauser had done this experiment. So at the Nobel Prize party, if Aspey and Clauser win, they're going to put them on separate sides of the table because they don't talk to each
He
other.
already got the Wolf Prize, I suspect.
All of them.
The Wolf Prize.
All three of them. Clauser, Zeilinger, and Aspey all won the Wolf Prize, I think. Maybe I'm thinking, maybe it's a
Was it
different prize.
Clauser the third guy? I'm not sure.
Yeah, but all three of them have the Wolf Prize now.
Yeah.
Yeah, so I think the bet is that Zeilinger, Clauser, and Aspey will win the Nobel Prize, but they're going to put Zeilinger in the middle and Clauser on each end of the, no fights. Okay, so now I could give you the entire history of entangled photon production. We move on from these cesium atoms that produce a few entangled photon pairs per second, and then this is 1980. Okay, so then we go to the on to the Zeilinger experiments where they crank up the amount of photons that are coming out. Heisenberg has this in his lab. You guys have parametric down conversion at Weizmann, right, 80?
Not in their lab.
In the next book, okay. And they make brighter and brighter and brighter sources. So now, these sources, instead of a few tens of photons per second, produce a billion entangled photon pairs per second. If you believe Penn, that's what's on the satellite, okay? So I could give you all of these experiments. Zeilinger first did this over several hundred meters to rule out to any influences moving faster than the speed of light. And then he did another experiment between two islands in the Canary Islands off the coast of Spain, Spain-ish Africa. So if you're Zeilinger's experimental student, there were two entangled photon experiments. One was between two mountains on two islands off the coast of Spain. This was very nice in the summer. When you're not taking data, you go to the beach. There are bars. It's a tourist place. Lots of wine.
You can take data while you're in the
You could take, yeah, you could take on your phone, okay? So if you're a good student of Zeilinger, you're sent to Spain to the island. The other entanglement station was at a sewer pumping plant in the middle of the Danube River, and the fiber optics they had to pull through the sewer lines in hazmat suits and then sit there taking the data in the sewer. So if you're a bad student, you get sent to the, and this is in Vienna, Austria, so the sewers sort of have several thousand of years worth of accumulated sewage, so this is not good to get on Zeilinger's bad side. Okay. So, all the way up, Canary Islands held the record for this entanglement test to distribution, 143 kilometers for a number of years, and then it was beaten by China from 143 kilometers to 1,200 kilometers. So this is the Chinese satellite Mozi, and I took this with my phone as it flies over this station. It's right over my office at USDC. And when they actually put this thing on the roof, it was this is China, you know, the roof, the guy tells you the roof holds, but maybe he pocketed some money and put inferior concrete. So I made sure to work from home that day when they were putting it on the roof in case it came through. But you can see it's stable. And this is, I put time-lapse photos, so I'm shaking a little bit and the students are moving around. But you can see this streak, the green light is the satellite tracking laser, and it's pulsed. So they have very good angular resolution, okay, so the telescope here is tracking the telescope emitter on the satellite. Now you can't see the entangled photons because they're too weak to see, but you can see the tracking laser. This is the green coming down, and the red laser is another tracking laser that goes up. So by doing a double lock tracking system, we proposed some experiment to NASA in the 2000s. They said we could never align the satellite to the ground station at this accuracy, but the Chinese figured out how to do this. And so this is a pulse thing. So if you look at better resolution, you can see it's actually streaked. It's dot, 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 like Morse code because it's pulsed. And the same thing with this guy here. Now the funny thing is that this telescope is about yay big. The entire satellite, the payload, each payload, there are 3 of them, are about the size of this table. So imagine 3 tables, and then you put solar panels on it. And what was I saying? The pulse laser, the entanglement pulse laser, they're going to make a point. And the telescope is yay big. Okay, so it's green light. So when it diffracts, by the time it hits the ground, the spot is about 1 kilometer in radius. Okay, so they're all. This is out in the middle of the suburbs. So there are all these Chinese people that live out in the suburbs, and if you're within the kilometer spot and look up, you see that. If you cross the street, you're outside this spot and you see nothing. So these stories about these Chinese housewives talking to each other, did you see the green spot that goes over every night at midnight? And the other housewife says, I don't see anything at midnight, you're crazy. Okay? Diffraction. But you can see this with your eyeball. So since it's right over my office, they call it the Dowling. Okay, so we talked about this test where we send the entangled photons and we run the Bell test, okay? And this can be used to, well, this proves quantum mechanics is right and Einstein is wrong. You can also run a cryptographic key off of this, not the one that you guys are using, which is the Bennett-Brazard 84 protocol, but there's an E91 protocol, which is slightly better for a number of reasons, but this is not a talk on cryptography, that you can use. And so, one of the ideas is that you establish entanglement between the 2 ground stations, you generate a secret key, one-time pad, even though nobody uses it, and then you use that to transmit your information securely over the classical internet. Okay, so let's look at teleportation. So here I have 3 photons. I have the entangled photon pair produced here from the experiments I just described. And then I have another photon here, okay, with an unknown phase. And I wrote it sort of, I'm taking, you remember my block sphere? We have altitude, what is it? This angle.
Elevation.
Elevation and azimuthal, right? So I kicked out the azimuthal. So this is an arbitrary unknown state. U is for unknown or U-boat or...
Light on for a second to take a picture of you in the lines. Okay, fine, go on.
I see the light.
Come to the light.
Anyway, so this is a photon with an unknown polarization state. And the idea is I want to transmit it to Bob. And Alice and Bob could be separated by 62.4 light years, which is the distance between Alpha Centauri and Beta Victoris, 2 of the nearby stars. Okay? So the first thing is the source sets up an entangled photon pair. And you don't know, Alice, this is a slightly different one, it's HHVV. So if Alice measures an H, Bob gets an H. If Alice measures a V, Bob gets a V. But they never know in advance which one it is, okay, because of the entanglement. So the idea here is you take an unknown polarization state, horizontal and vertical, some superposition. So the unknown parameter is theta. Now what is theta? Theta is the phase of my qubit. Remember, for the past 2 weeks I've been yammering on about this phase when the qubit oscillates around like this. So this is a qubit with a phase theta, okay? And the qubit is not the important thing, it's the phase which carries information about my sensor. Remember the phase? All right. So if I have a sensor here that measures the phase, maybe it's time, maybe it's magnetic field, maybe a gravitational field, and I want to get that phase information to Bob, I cannot measure this because the collapse, the uncertainty of the quantum mechanics causes a collapse, and then I lose the phase information. So I cannot measure it and then send it on to Bob. And if I only have 1 copy, then I'm screwed because I totally destroyed the phase. So what I do instead is I take the unknown phase qubit here on Alice's station, and we mix it with 1/2 of the Alice-Bob qubit. So in the actual experiment, there's 2 photons that come in, and we have some polarizing beam splitters, and Leo, what else do I need? phase plates and blah, 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 but it's all linear optics, okay? If you do it with linear optics, this works half of the time. You make a measurement, and the measurement has, if you do it perfectly with nonlinear optics, you get 1 of 4 outcomes, okay? And I'm not going to describe which of the 4 you get, but 4 outcomes, you can encode those in 2 bits of information. First outcome is 0, 0, second outcome is 0, 1, third outcome is 1, 0, fourth outcome is 1, 1. So 2 bits of information. So when this measurement is made, this is gone. This precious phase-carrying state with our sensor information is destroyed. However, it instantaneously appears over here with the phase, which is my sensor information. Okay? Now, instantaneously is sort of up for grabs. It shows up over here, but garbled. It's in 1 of 4 possible different states. So Bob has to put this in a quantum memory, which could be an NB diamond or an ion trap or some other solid state or superconducting memory, and holds it until he gets a classical message from Alice. Was it the 0, 0, the 0, 1, the 1, 0, or the 1, 1? If it's the 0, 0, he does nothing, and out pops the state. If it's 1, 1, he applies a rotation. If it's 1, 0, he applies a different rotation. But these are just rotating beam splitters and so forth. So at the end of the day, he gets back the original state, and this one is destroyed. So you can't use this to send information faster than the speed of light, because he cannot. If he tries to extract this state without this classical communication, he gets garbage. He just gets random noise. And you can send random numbers faster than the speed of light because they contain no information. But in order to reconstruct the state, Bob has to wait for this classical signal that moves at the speed of light or less. And so, teleportation sounds crazy, like Star Trek. Okay, the Motzi satellite has demonstrated this. Again, the previous record was between the Canary Islands, 143 kilometers. Motzi has demonstrated over 1,400 kilometers, 1,400 kilometers. They teleported an unknown state of a photon from a ground station up to the satellite. Longest distance, 1,400 kilometers. Not quite Alpha Centauri, but moving in that direction. Okay, so the critical thing for what we're talking about here, if this is a qubit that's carrying a phase information theta that has sensor information, and I would like to collect perhaps an array of sensor phases at one station and combine them coherently, the best thing to do is to teleport the qubit from point A to point B. Now, a couple of points. When I measure this photon, it's gone. I don't send the photon from here to here. I send the state of the photon, which is the phase information, from here to here. In fact, I could teleport a photonic state onto an ion trap state, or even one, God forbid, one of Katz's superconducting systems. And it doesn't matter what the hardware is. It could be ion, photon to ion, ion to ion, ion to superconductor. The critical thing is that you end up with a qubit that has this phase. So the particle, people say, I teleported the photon. It's wrong. I teleported this quantum state of the photon, which is this phase information. The photon itself is destroyed. So here, has watched Star Trek. Anybody? Star Trek? No Trekkies. But you know enough to know they have a teleporting machine, right? Okay.
Not Scottish.
You never watched Star Trek?
No, I thought beam me out, Scotty.
Beam me up, Scotty. Okay. So, whenever I give a talk about teleportation, or Jeff Kimball gives a talk, he's a famous professor at Caltech, he says, never should we discuss Star Trek, because that confuses people. So I, of course, always discuss Star Trek.
Is there an inherent error in this process?
Not if everything's done perfectly. There's no inherent error. And I'm not violating Tomer, the no cloning theorem, because this state is not a copy. I must destroy this state before this state shows up. So at any time, I only have one copy of the state. So people say, oh, it violates the no cloning theorem. I have 2 guys. No, I killed this one. So this brings us back to Star Trek. In Star Trek, I don't send Captain Kirk from the spaceship to the ground. I copy all the information required to build a Captain Kirk I destroy Captain Kirk on the spaceship, and then build another one on the ground.
3D printing.
3D printing, right, but very advanced, okay? And so it's exactly like this. I destroy this one, and I create this one, but this is on a photon, this could be on an ion, but it's still, the phase of the qubit is Captain Kirk. Now, I'll give you an example why classical and quantum is different. There is in the Star Trek New Generation, they have Commander Riker is on a planet, and they're trying to teleport him out, okay? But there's a teleporter malfunction, so that, and they have noiseless amplifiers and all the things that you can't make in your radar system, okay? So there's a malfunction where they teleport Commander Riker over here, and then they use the amplifier to reconstruct him, but they leave another Commander Riker back on the planet. There's two of them running around at the same time, which is a great plot twist. So he lives in this cave on the planet for 7 years before they figure out what's gone wrong. And the other Captain Riker gets married to the beautiful girl, and so the one in the cave is very angry, and he joins the rebellion. It's a good plot twist. But that can't happen quantumly because of the no cloning theorem. There can never be two Captain Rikers. Okay, so all the way up to the no cloning theorem, it's a lot like Star Trek.
There is only one different difficulty associated with that, is that at A, you can never get a Bell measurement that distinguishes all possible for.
You can if you have a nonlinear gate. If I have a C0 gate for photons, I can get all four. It's only if I use linear optics alone, then I destroy 50% of the time Captain Kirk dies. So that's why you want to move from linear optics to Katz's system, where he survives 99% of the time. Now, so with linear optics alone, you can this only works half the time. But if you have one nonlinear gate, like the one made at the Weizmann Institute in Barak Dayan's lab, you have a C0, then it works perfectly.
So I have a question. Maybe there's a
This is
mistake here, but
80 Pick from Weizmann. She drove the bus.
and it's a question about this atom that Barak has in his lab. So if you can take a photon and do swap in, swap out. So you take an atom, it writes the state of the photon, and then you bring another photon, and it reads the state of the atom, goes to Bob, and then Bob swaps in, swaps out. Do you still need this? I mean, you just transfer the photon, if you're allowed to use.
Right. So what Addie is saying, let me simplify it. Why doesn't Alice just send this to Bob? Right? That'd be easier than doing all this entanglement stuff. So the point is that, and this is actually a critical question. So the point is, the entanglement contains no information about the state. It's a resource, like the electrical outlet in the wall. Okay? So I can send the entanglement over and over again, and Alice and Bob know when they get the entanglement, and sometimes it fails because this is diffraction and all this other stuff, and it's going a long distance. So it doesn't matter if the entanglement fails, I just try to send it again. And I send lots and lots and lots of entangled pairs, and then there's something called entanglement purification. Even if I get crappy entangled pairs, I can make them pure, pure, pure. And once Alice and Bob are sure they have a wonderful pure set of entangled states, then they do the teleportation. So Captain Kirk sits there and waits until the transporter is functioning properly, and then goes. Where if it's a lossy channel, maybe 50% of the time again, the Captain Kirk is lost. So you wait until your resource, the entanglement, is in place, and then you teleport, and that avoids a lot of the noise and loss over the channel, because the resource that you're transmitting, the entanglement doesn't is robust in the sense you can just keep rebuilding it and repeating it. We'll talk about it in a second. So that's why you don't want to just send the state. This is critical for the quantum internet. Okay. So this is the Entanglement 2.0. All right. So what I'm going to do now is I have two teleportations. I have an entangled pair here between Charlotte and Doug. My dog's name is Charlotte. And then Cassie. Cassie's the new dog. Okay. Alice and Bob. So the idea is Alice has an entangled pair here with Bob. Charlotte has one with Doug. They do the Bell measurement here. And what happens is that the state of this photon is teleported here, and now Alice and Doug share entanglement. Okay? This is called entanglement swapping. And the cool thing about this is that this photon never talked to this photon. They were light years away, right? That one went that way, they never crossed. but the Bell state measurement teleports the entanglement. It destroys 2 photons, and at the end, these 2 guys are entangled. So that's a way you can go to longer and longer distances by putting in additional Bell measurements, additional sources. This is something called a quantum repeater with a little extra stuff. All right, so this is quantum networks. This is just a quote saying that I'm famous. Okay, the editor says I've been stealing graphics from Wikipedia, and they said we can't always get the rights to the graphics from Wikipedia. And I know that's what is it? It's the open release GNU license. They don't know what that is. It's much better if you take pictures from Shutterstock, because we have a license for that. So this is Shutterstock, which hopefully they will remove this in the printing. Okay, but anyway, this is supposed to be an entangled network. Okay, so let's start out with the telephone system. Now, I don't know how telephone systems evolved in Israel, so I'm going to give you the American version, and since you probably don't know how telephone systems evolved in Israel, we'll be fine. Okay, so in my house, I still have a landline, and the students laugh at me. Dowling has a landline. Why don't you just use your cell phone? Well, I don't get very good reception because I'm at the edge of the city. And the other thing is that
finding the cell phone.
Well,
it's used for finding the cell phone.
the landline, yes, it's useful for finding the cell phone. But even more useful, we have these things called hurricanes. Come through, floods. The first thing that goes down is the power grid, and the cell phone towers go down. And then my charger, I got maybe a day worth of power on the cell phone, and I'm screwed. Again, I'll communicate. And even if the cell phone is charged, the cell phone tower is out, I'm dead meat. The landline has its own power supply. So back in the 1800s and early 1900s, the telephone company said, look, we want to sell telephones to as many people as possible, even people who don't have electricity. So we will give them electricity from the central station. What is it? It's a few volts on the landline. So when the hurricane knocks out all the power in my house, the cell phones are out, the landline, I pick it up, it has its own power supply. That's the resource, the power supply. Now it might be noisy because of the hurricanes and the floods, but I can still dial and communicate, okay? So the power supply from the phone station is like entanglement. It's a resource. Power supply, I plug in my phone. Entanglement, I plug in my quantum memory and accumulate entanglement. So how did this work? Well, we had a central station, and all of these guys have a small voltage amp wire connecting to their phone. This is a Swiss phone. I couldn't find a good American one. So in the old days, we had a receiver, and this one actually had a battery in addition to the power supply and a crank. There's no dial or anything. So you crank it. You've seen this in old movies. And that crank sends a signal along the phone company's electrical line to the station. And their person picks up the other end, rings a bell, and goes, hello. In Sweden, I guess, what is hello in Swedish? Snacka du norsk? No, do you speak Norwegian? It'll be something else. Hello. Anyway, they say hello. And Alice says, I want to talk to Uncle Bob. Okay? So at the station, the person unplugs the cord from Alice's port and plugs it into Bob's, turns a crank, which sends a pulse along the electrical line, and Bob's phone rings. It doesn't have a dial. He picks it up, and the operator says, your niece Alice is calling, and then she lets them talk. That's how it works. Okay. So, and this is a star topology where you might have a city, and the station is here. This is very complicated with the switches and the power supply, and maybe these guys don't have power supply. But the station has two jobs. It sends out the power to the landline, and it does the switching. Okay? So we're going to do exactly the same thing with quantum entanglement. So the idea now is the station, Alice pays instead of for the electrical power. So I pay my phone bill whether I use it or not for the landline, right? I pay a set $100 a month for the landline. Okay? Even if I'm not making any calls, I'm paying for the power that's coming to it and the right to use it. So, same thing with the entanglement. I pay for the entanglement distribution, so there's an entanglement source here. Source keeps part of the entanglement in memory, and then sends the other half of the entangled photon to Alice, which she puts into her memory. And you accumulate it maybe don't use it right away, like the power line. Then one day, Alice says, I want to teleport a precious sensor state to Uncle Bob, or I want to establish a quantum key with Uncle Bob, or I am in the midway through a quantum computation, and I need to send part of the quantum computation to Uncle Bob's quantum computer so we can do parallel distributed quantum computing. All of this means I have to send the state, okay? And Eddie, you don't want to send that precious state if it's the result, part of the long, elaborate quantum computation, if it's going to die half of the time. So what you do is you establish entanglement between Alice and the station, and then Bob and the station have their own entanglement established. She calls up on the classical landline now and says, I need to share a quantum state with Uncle Bob. And they go, sure, you paid for your entanglement, you have plenty, okay, at your end. So what they do then is that the station does the swapping. Remember the swapping on the previous line? Which is just a controlled set of control NOT gates. And at the end of the day, Alice and Bob share a whole bunch of entanglements and the station is out of the picture. And then they can do whatever they want. They can send part of a state for a sensor, a state for a quantum computer. They can establish the Eckert 901 cryptography protocol, whatever you might want to use for entanglement. And eventually we'll have room temperature, NV diamond memories that you can put in your cell phone. So when you plug your cell phone in at night, in addition to charging it up, there'll be a storage of entanglement on your cell phone, which you can then use. I predict this is 100 years away, which probably means 10. Okay, whenever I predict, I always over-predict. But the bottom line is Alice and Bob share entanglement. And there's a critical point here. The station knows nothing. At the end of this protocol, the station knows nothing. So if I'm going to set up a cryptographic key using Alice and Bob entanglement, the station is out of the loop. And you can prove the station is not cheating you on the key. How do you do this? Alice and Bob periodically run this bell test. Remember the bell test? 2, root 2, 2, okay? If the station is sending false entanglement or cheating or there's an eavesdropper, the bell test goes below 2. And you catch the spoof, okay? But if it's above 2 root 2, then you know that nobody in between knows anything, and you can tell the general with the nuclear missiles that it's secure, and it's called device independent. So right now the Chinese satellite, it has one cryptographic downlink. It uses the same thing that you're using in your lab or your company, the BB84 protocol, where they send attenuated pulses down. The satellite communicates here, then it sends another set of sequence of random numbers here. It does an XOR operation. Alice and Bob share key, but the satellite knows everything. So the American military would not use this because the satellite knows everything.
They also
The Chinese satellite.
The Chinese also did Eckert for 1,500 kilometers.
Now, I knew about that 6 months before it was published.
Because you're great, but they did it.
I am great. No, I'm friends with Pan, so he always says, here's the data.
Yeah, but the problem of the device independent that it has to, it's limited in range at the end of the day.
Well, yeah, okay, so that's, you need repeaters and so forth. But the point is, if the satellite is sending the entangled photons, and I establish my key using the entangled photons, I can run the bell test and show the satellite doesn't know anything. Now, maybe the US military won't buy that. Okay. So here's how the setup goes. Alice and Bob, this is what I said. Alice shares entanglement with the station. Bob shares entanglement with another memory in the station. Then there's their entanglement, memory 1 and memory 2. Entangled pairs, we do the swap gate, and then at the end of the day, Alice and Bob share lots and lots of entanglement to do anything they want, and the station is no longer in the picture. So depending on some additional proofs, you can show the station doesn't know anything as long as it's not too far away. All right, so I think it's time for a break, right?
Yeah, I was going to suggest.
I know.
10 minutes.
10 minutes.
Do you want I'll bring you a coffee from downstairs?
No, I just need a water. I think I forgot. You're not coming to dinner, though? Probably not. No. Yeah. See you next time.
Good to see you.
Okay. All of the different points. Oh, I mean, great. Leaving? Bye. Yes. She was actually ahead of me.
Oh, sorry. I didn't see you. Very, very sweet.
He's just impressive as he's tall.
Oh, my fault.
Tall Lawrence is just standing.
פתרתי בעיה.
Yeah. So what?
עד שזה פה, תמיד אני שאל את עצמי, התפגשו, התחתנו,
So you need lots of them. The idea is you have lots and lots of entanglement. And then you use maybe 10% of it constantly in the background for cheap. But then you save the other 90% for doing your work. So they actually do this under Lake Geneva. So they have Entanglement Source on an island and they constantly run this stuff. And then they do things to make it look like it's an eavesdropper. And then the number immediately drops. Even better, they have to align these fibers to within a few vectors. So what they do, if they're not aligned, they'll fail the vectors. So they adjust the delay lines between the fibers until it goes above 2, and then they know they're aligned, because otherwise they use it as an alignment. But it's always, the idea is they always run this in the background, some fraction you're sacrificing continuously, and the eavesdropper would have to know which ones are going to use actual data transmission, which ones are going to do the test. So you do it random. You don't say which ones are going to do it. So that way
כיוון שהפונקציית גג, המצבים האלה,
she tries, the number always drops. That's the proof that a guy and I are arguing about my number. If there's any tendency, it goes below 2. It's called the right system, and it takes care of it. You save the device, Swiss, Israel, and you trust it. I don't think Americans will ever use a Chinese satellite no matter what I should
זה שווה לאחד, סכום כזה צבוע שווה לאחד. זה המצב, יש לנו מצב חצי, מצב פלוס חצי, מצב מינוס חצי. זה כמו תחשוב שיש לך מיטה. יש לך אינסוף מצבים, אבל דידי יכול להתנדנד ככה, ואיזה יכול להתנדנד ככה, ואיזה הוא שוב. שעשינו יותר רק בשווה כנגדים, אז יש לך אינסוף מצבים. מצב שהאורך של המיטב הוא חצי גל, מצב שהוא אורך גל שלם, וכו' זה וכו' וכו'.
Okay. So
I told him to solve me another problem. That time I'm thinking, yes, will Alice and Bob, will they meet, will they get married? And son said, no, she's the niece and he's the uncle.
Yeah, we can write a movie script.
אז מצב, יש לך אלה וקטור, כאילו זה פונקציות בסיס, הסינוסים, או הקוסינוסים, אתה יודע, איפה אתה שמת, נניח שאתה שמת, זאת אומרת, הסינוסים והקוסינוסים, כל האורפיגל השונים, הם המצבים שלך למיטה, ואם אתה מתחיל למשל באיזושהי צורה כזאת, שהוא נתן את הסרט הזה, כשאתה רואה מיתר, אתה לוקח שם מיתר, לא, זה משהו אחר. אתה לוקח עכשיו מיתר, אתה מושך אותו פה, הוא מתחיל בצורה כזאת, אתה משחרר אותו. הפונקציה הזאת, זה קומבינציה, אתה עושה פירוק פוריה למעשה. זה פונקציה, לא, זה הפונקציה הזאת, כל אחד עם המקדם שלה. בתוך המרחב הוקטורי הזה של קוראים לזה מרחבים בתוך המרחב הזה, הפונקציה שלך היא קומבינציה הרבה פונקציות. אז אותו דבר, פונקציית הגל זה כמו תכתובת מיתר שיש לך הרבה אופציות וקומבינציה שלהם.
בכל אופציה זה מצב?
מה ההבדל זה שכשאתה לוקח למשל את הפונקציות של המיתר אתה עושה מכפלה סקלרית ביניהם. מה זה מכפלה סקלרית? אינטגרל של פונקציה אחת כפול פונקציה שנייה, אז זה בסיס אורתוגונלי.
You guys have the same office.
Not exactly. No.
I'm leaving. This is my last night.
I know. Oh, really?
Yeah. So he wants to ask a question. You wait.
Okay.
Okay.
No problem.
What is your question?
I ask what I asked before. If there is 3dB plus the attenuation, you said it doesn't difference if it's the attenuation of the environment or
Yeah. We don't care.
But if we're in the vacuum, in the space, so we don't have the last.
No environment, but you still have the so
It's not 2dB.
Nobody said it was 3 dB. I said if it's greater than 3 dB, you're screwed. I didn't
It's better to use the coherent.
It's better to use the coherent state and not the new state. That's just what the math predicts.
3 dB is only if higher is the current state or lower is the
Yeah, exactly. So the new state goes well up to 3 dB, 5, and then above 5 is the coherent state. But it still doesn't matter if the loss is from scattering or from diffraction. Once you hit 5 dB, they help you. That's the point of the paper.
But also you can use the MNN.
Yeah, but still 5 coherent states, around 5 or 6. Any quantum trick to try.
I have another question about the entanglement. I started asking, but Sam stopped me to show you because if this is the seed, the island, okay, it's like this. If I would go, if I check, I forgot the name, if I check the signal over here, the island over here, so I need to sample. Yeah. If I sample the island over here, so this is important to see if the two signals are correlated and entangled. You need to time them and sample at the same time.
Exactly. Let me show you what the Chinese do. The Chinese, they start off with 10 to the 9 photon pairs per second. Okay? So these guys are coming down like this. There's lots of diffraction and that. So, but they're pulsed. I'll say one every nanosecond. Okay? So you expect to find a photon pair each nanosecond time. 1 nanosecond. So now when you get to the ground, you might have 1 photon here, 0 here, 1 photon here, 0, 0. Mostly you're going to have 0, because you're lost. Every once in a while, but sometimes you'll get a 2. Okay? The critical thing is if you get a 2, you need to make sure this guy is paired with this guy, and not with that guy. Right?
No, sorry, can you say it again?
Yeah, just what you said here. The time needs to be the same, right? So, because of atmospheric fluctuations between the ground stations, this one might arrive a little early, this one might. So if this one correlates with that one, we'll get those signals, okay? So this time meaning is like 1 nanosecond. So, and they have synchronized clocks on the ground stations. And so they know exactly when to expect a pair.
How they can expect a pair if the target is moving?
This is the whole point. Brilliant.
Something which
They have the clocks on the ground. They're synchronized. They're synchronized with the clock orbit. The clock orbit is moving. But remember that I showed you the green laser and the red laser. Red is going up and green. That's also time.
but they only can do it if they expect the target to be over somewhere. They can do it if the target is...
Well, this is not a target. This is the satellite that they control. They know exactly where it is.
So they time because they know exactly which is the...
They own the target, so they have one advantage we do not have.
So it's not a red one, it's a communications system.
Yeah, it's like you time in everything.
No, I mean, because the satellite, I know this project. I talk about Racah. I want to know if I can search, and if I can search, that means I can count on the time. I don't know when the time is.
Well, that's where, but you can, because what you do,
And actually, this is doesn't belong. If you use 10 of a 9, okay, and in the
classic, I use 10 of the 20.
But over here, you still time.
No, what I wanted to ask, I said this is what I know that you need to do to check the environment. What I want to ask is if there is any other way to check the time except time. There is any properties which isn't
Time
yeah, time.
now, because of this issue, right? I mean, you still need the photons to arrive at So what they do is the photons are actually, if I don't know the timing, I put a delay on the timer. So I start to delay right? And then I run this test. Okay? If the signal and either are not at the same time, I get data down here. But when they are online, then I get data down here.
הוא מעביר לנו את המידע. כן, זה צריך להעביר אותו.
But the point is, so what they do is they put a delay on it. So they don't have the time to so they just adjust the time of arrival and monitor this. A half a D. So they do this, and then if they're not aligned, okay, and then it does actually does this. And then you know they're aligned. And now you know the focus. Otherwise,
for the first time you make after the first time you know where it's at.
yeah.
But it's not delay, but it's I don't know if I can count on that because I need I don't know, like 10 hours of measurement or I don't know how fast. So it will be correlated to
Yeah, so this I'm going to give you the opposite. So they have a system where the Entangled Source is under an island in Lake Geneva in Switzerland. Alice is in Geneva and Bob is in Lausanne. Okay? And they have the fibers running under the lake, but there's temperature changes and the fibers change. So they have to align the fibers first to make sure that if there's no fault, they see the delay line so they put a delay line, and they adjust the time and they monitor this, and then when they are aligned up here, they will stop. But then they have feedback that always makes it up here. They can just get
so you count on the first time because I do have a chance that I have correlated because I have got I can jump to the quantum state.
This is what we were talking about in the owl today. We said we didn't use the bell violation. This is the bell violation. He said it would work, the guy said it would work, and I said it would work in the optical, but I don't know if it's microwave.
The guy says something that I don't understand.
Okay, you have a question after the next. You wait. Okay. Where is it? Tax. Romberg. Is that even a word?
The cat.
אני יכול לעשות את זה בקוונטום אילומיניישן, לא ספיד יש לך מיד ואתה מתחיל לעשות קורלציה.
Alright, we should start this, the last hour of the last hour of the last hour. No remorse. Okay. So this relates. They ask questions and then I give the answer and they're looking at their phones. Give me the phone. Give me the phone. You take notes. In my class, I tape the phones and I stack the pictures. and the students are staring at their phones. You're looking at your phone, and then they see their phone, and then they begin to sweat. And it's like, I'm going to miss one message about lunch. I'm dying. Okay, so
Monty Python, bring out your phones.
without the phones, right? Okay, so now I have a bunch of local area networks, okay, star graphs, and I want to hook them together. So your question is, how do I go long distances? So again, the answer is entanglement swapping plus a quantum memory. So this is supposed to roughly look like the United States, but I suppose if I turn it this way, it could roughly look like Israel. But the point is, these guys are far apart, right? Yeah, I have to do a mirror image reverse and then rotate.
For Russia.
For Russia, it could be Russia. So the point is that there are things called quantum repeaters, and the standard quantum...
Are there?
There someday will be things called quantum repeaters, which are, every element of a quantum repeater has been demonstrated except for the memory. If we have a memory, tomorrow somebody solves the memory problem, we're ready to go. And then there's another approach that the Weizmann they're gone looking at, where you use highly entangled cluster states, which I'm not going to talk about, and you don't need the memory. But the point is, you're going to put. So what do we do in the classical network? In the classical network, I'm sending pulses, 1.5 micron over the fibers, right? That's a classical fiber network. And those pulses carry information. And those pulses, the amplitude of the pulse gives you 0 or 1, right? I think it's, if it's double, it's 0, or 1, or it's horizontal, it's 1, and I don't know what it is. Okay.
It's much more complicated.
It's much more complicated.
It's in phase, and it's
phase and everything.
distributed, whatever.
But the point is, the photons are subject to loss in the fiber. The loss in the fiber, you lose, if you go, even with the really best fiber, if you go 11 kilograms, you lose half your photons, okay? So a few 11 kilograms with an exponent.
Kilometers.
What?
Kilometers, not kilograms.
It's very hard to go kilograms.
Kilometers. The last day. Give me a break. Kilometers. So they have repeaters. So two breakthroughs occurred in the 1970s. One was Corning made very low loss fibers at 1.5 microns. It would go very, very far. But the other one was they made an amplifier that's essentially a laser LED LED that sits in the fiber, and they put them every few hundred meters, and when the pulse comes through, it is amplified, and then it goes weak, amplified, and then weak, amplified. Problem is, you think, well, why don't we just do this with the quantum ones, okay? The no cloning theorem, or the no non-noiseless amplification theorem, says you cannot make a copy or duplicate an unknown quantum state. So if you send quantum states of light carrying entanglement or quantum key distribution or anything, through the classical amplifiers, you just get random noise out. It destroys the quantum state, particularly that phase, that is my sensor phase. Everything is gone. So the quantum repeater is much more complicated. The idea is you do the entanglement swapping, swap. So everybody has a memory, and so Alice tries to swap with Bob, Bob tries to swap with Charlie, Charlie tries to swap with Doug, and Xavier tries to swap with Zebediah. 26 letters in the English alphabet. Can I finish my hand dance here? So they're all trying to swap with their neighbors. If it succeeds, they put the entanglement into memory. If it does not succeed, and then they announce over the classical internet, I have Bob and Alice share, and then when all of them have succeeded, then they go swap, and then Alice and Zebediah share entanglement, and nobody in the middle does, and you can go long distances around the Earth. Where did he come from?
John?
Lost. Yes?
Shouldn't stimulated emission be exactly what you're looking for? You produce like another photon.
You cannot have stimulated emission without spontaneous emission. That is a statement of the noiseless amplification. So it's impossible. Classically, you could have noiseless amplification. But quantum mechanically, you always have spontaneous emission, and that kills you. It doesn't kill you at high pulses, but at single photons, you're dead. Because you get one spontaneous emitted, and as the esteemed Professor Cox said, it has something to do with phase and all those other crap, right? The phase of the spontaneous emitted photon is random, not in the same direction as the stimulated, so it's noise. And so you can't, spontaneous emission is a fact of life. If you don't have spontaneous emission, in the Einstein laser rate equations, then you don't get the Planck black body formula right. So Einstein was smart. He said, okay, I have the rate going up. This is stimulated absorption. And I have the rate going down. This is stimulated emission. And then he calculates the different probabilities and tries to fit it to the Planck blackbody curve. If you don't add the spontaneous emission, you get the Rayleigh-Jeans curve, which blows up and everybody knows is wrong. So Einstein said, okay, what do I have to add to this formula to get the blackbody curve? I add an additional spontaneous emission term. He doesn't know what it comes from or anything. But if you add that, then you solve the equation, you get the Planck law. If you don't put it, you get Rayleigh-Jeans, which is wrong. Okay, so there are many reasons why spontaneous emission, you can't just ignore it. Without it, physical reality collapses. Okay, so no non-noiseless amplifiers means you do something else. But it's the same trick as we do with the, remember you asked, why don't I just send the state? Or maybe she asked, somebody asked, yeah. Why? Well, the state is very precious, and there's a lot of noise, so what I do is I wait and wait and wait. Everybody shares entanglement, and then we do the entanglement swapping. We build up lots and lots of entanglement. If it's noisier, I might have to wait longer. Purify the entanglement, and once Alice and Zebediah share good entanglement, then they teleport the state. Okay? So, if you have a quantum repeater, which is every element of the quantum repeater has been demonstrated except the memory. So, if I have a memory at 1.5 microns, I just plug it in, and we got a repeater. And people are looking at the
every element except the only important one. The only one that matters.
Well, doing all of the entanglement purification and all of that is pretty complicated. Anyway, so that's how we go long distances, okay? And now this is something I told my undergraduate engineering students. At first they don't believe me. So in the classical internet, it used to be when I was a kid, I called grandma when she wasn't busy at the window, like his grandma. Sometimes it would go over the copper wire, the landline, and I would get a good signal and talk to her. But sometimes it would go via communication satellites because the copper wires didn't carry a lot of data. And then you get a weird delay. You're like, hello, Grandma, and then you have to say, over, and she goes, hello, Johnny boy, over. You know, because of the delay, you couldn't talk normally. Then around the 70s and 80s, this went away because everything went over optical fibers. There was no delay. So now I tell the students there's optical fibers running under the Atlantic Ocean, right, all the way from the U.S. to Europe. And one of the students says, you just drop the fibers into the ocean and that's it? And I go, yeah, that's it. And so now I have a question. So it's actually bundles of fibers, and they contain a certain.
It's like a meter.
It's about a meter long, okay, and there's billions of fibers in there with a coating. She was thinking that it's just one fiber the size of the hair going across the Atlantic Ocean. And I have a question. There's repeaters every few hundred meters.
No.
For every few kilometers.
No.
Yes?
It's 50 to 100 kilometers.
Okay, fine. In my book, on the theory, the few hundred meters is 50 to 100 kilometers.
You change it because people will make fun.
Okay, but wise guy. Every repeater has an LED. Where does the power come from at the bottom of the Atlantic Ocean?
What is the power coming?
The power of the LED for the classical amplifier.
There's a laser that runs a photo cell.
Yeah, they run the pump from shore. They use another fiber to run the pump.
Do you agree with that,
No.
Professor
No, it
Kepp?
doesn't make sense.
Doesn't.
Yeah, okay. You both failed my class, okay? There are a bunch of AAA batteries at each one of the repeater stations. I don't know if they're AAA. There's a battery. And the LEDs require so little power that the battery dies about the same time when the cable starts falling apart.
No, they're using optical amplifiers.
But
It's not a repeater.
something has to
Yeah,
power.
you have to pump it. It's much more power.
No, but it's a battery. Every repeater station on the Atlantic Ocean, there's a battery. And so I asked the students, well, you know, how did you got it wrong? It's a battery. I said it must be just a couple of AAA batteries. And so it's a battery about yay big in this big bundle. And then I thought, well, they have to go down in a submarine and replace the batteries. They go, no. When the battery dies, the cable is falling apart because the sharks have been nibbling at it, whatever. So we just replace the whole cable and run a new one with new batteries.
It's billions.
Yeah, billions of batteries.
That's billions of cost of replacing one of these.
Yeah, but that's
extremely expensive.
But they're batteries every 100 kilometers. So I didn't know that about the batteries. I thought maybe they run a copper wire with an electrical current running through it, and they're just batteries. So every repeater under the Atlantic Ocean class has a battery. Okay. So the idea here is that, eventually, right now the entanglement source on the satellite MOTSI is as big as this table. It's yay big, telescopes and everything. But I'm working on a National Science Foundation program where we're trying to make the entanglement sources on a chip. Big. And the goal is they will put out 10 to the 9 photon entangled pairs per second. And we do the Bell measurement on the chip. The detectors are on the chip. So the entire thing is a box, yay big. And if I have my quantum memory, which is all on a chip, put that on there. So my quantum repeater is a box about yay big, powered by a battery. And you put in your cell phone. Or instead of having a router next to your computer at home, okay, well, they don't have desktop computers. You have a router in your house to power your TV to watch videos. You'll have a Q router that will be distributing entanglement, okay? And entanglement will be a free resource. Everybody will have entanglement in their phones and in their house and on their laptops. And this is the day I look for someday. I told you the last lecture would be crazy. Okay? Whenever I predict something is 100 years away. Okay, so back to Grandma. Tomer, your question is, what do you do in empty space? Okay? You do this. So that the satellites are sending entangled photons down, but you can also send photons between the satellites, and then only the diffraction, because the telescope on the satellite is about yay big. The satellite on the ground is about 10 meters, okay? But if I'm going satellite to satellite, it's meter to meter, so there's a lot of diffraction loss, okay? So the way to overcome that is just to make the entanglement source brighter and brighter. So we're hoping to get, the Chinese say they're going to get the 10 to the 12 photon pairs per second. And we shall see. But the idea is that we have these stations now. Instead of running a fiber under the ocean, we don't have the repeater yet. And we do have the satellites. So the idea is to have a constellation of satellites sharing entanglement with the ground stations. And then I can hook the local area networks here, or the wide area network here with this one. And everybody on the Earth shares entanglement with everybody else. And it's just like the power in my landline. I plug it in, and it costs more to call long distance. So if instead of Uncle Bob, I'm calling Aunt Charlene in France, you pay extra because it costs more to get the entanglement over the long distance. Just so none of them know what it was like in a landline. You had to pay extra for a long distance call back in. Okay, so how do we do this? We have this setup. And the idea is that we have an entanglement source here, producing entangled pairs. I think that's the right one. There's an entanglement distribution center, blue. Okay, that's creating the pairs. And then I store them at memory at these stations. Okay, and now these stations get entangled with these stations through entanglement, the quantum repeater entanglement swapping. And then eventually everybody could share entanglement with anybody else. So this is the quantum internet. Okay. Now, how does the classical internet work? Suppose Alice wants to send an email to Uncle Bob. So the classical internet, don't give me grief, cats, okay, roughly, takes your email. Let's say, short email. It breaks it up into little packets. These are called TCP IP packets, but each packet contains a head. So it's like a fish. The head of the fish knows how to reassemble the information in the body and where it's going. Okay, and it swims through the internet, and then and there are many copies of the fish. So there are many copies of your email, and they're released, and now the fish swarm all over the internet. They arrive at Uncle Bob's desktop computer, and the computer reassembles the email. The fish heads know where each piece should go, and there are duplicate copies because sometimes the fish gets stalled. There's a break. Too much traffic here. Those fish never make it, but copies of the fish might take the longer path, okay? But what can I not do with quantum states? Copy. Okay. So the redundancy instead is to share many entangled pairs. And I can send the entanglement this way, I can send the entanglement this way. Maybe there's a blockage here, so we go this way instead. But I don't send anything precious. It's like the power line, okay? I wait until Bob and Alice have a lot of entanglement, pure entanglement, and then, using the classical internet, I can teleport quantum states from Alice to Bob, carrying my precious phase information, which could be used for the key or for a sensor. Okay, so it's a lot like the classical internet. In the classical internet, they get resilience to loss and breakages in the internet, redundancy, by making many copies. Okay, well, I can't make many copies of the state I want to transmit. That's the classical thing. So I make many copies of the entanglement, which is a resource. I don't care about that. And however it gets there, and I know when the entanglement is established, and then I teleport. So in any quantum network architecture or in a quantum computer chip, you always ask the question, classically, how do I move data around? Well, in a classical computer chip, you send the data over the wires, and it gets from point A to point B. Okay? If you study quantum networks, and you analyze this, it's always better than teleport than it is to send the quantum state directly. So most designs for quantum computing architectures and networks is just a big entangled network, right? So teleportation has gone from Star Trek to the preferred protocol for moving data around on a quantum computer or quantum network. So it's reality. It's not just beam me up, Scotty. Okay. So this is what we will do.
John, it's always two-body stuff, and never anything useful out of 3 or 4 body interaction?
That would be another chapter at another talk. So I'm avoiding the 3-party states. The 3-party states, right now, we're studying, I have several, this is from my paper published. And the satellite was also from my paper, just submitted for publication. So if you send multipartite states, 3-particle, GHZ states. Remember the particles that had 3 entangled spins and so forth? It's not clear exactly what they're good for. There's a protocol for making better synchronized clocks, but it's not really exactly what I would want. The W states, which are the other class, they seem to be more robust. GHZ states are very susceptible to noise and loss, just like Noon states. If you switch to the W states, they're resilient to noise and loss. This is another multi-part. So instead of talking about HVVH, we're talking about HHHHH plus VVVV, or HVVVHHH plus VVHHVVV. And so the W states, they're resilient to loss, but they don't seem to be much good for anything except generating bipartite entanglement. So you might as well just start with, so we're doing, keep it simple. Okay. So I'm a little early. Okay, so Charlotte's Web. And so the title of the book is Schrodinger's Web, which is the quantum network, right? The new book. So this is a mandatory reading. If you're a child in the United States, this is a child's book. Okay.
It's a sad book.
It's a sad book. Okay. So for extra credit, one of the creatures in this picture is Charlotte. Which one?
I know the answer.
Everyone knows.
You know?
Of course.
The spider.
I mean, it says Charlotte's Web.
Well,
Pigs don't have a web.
But it doesn't say the spider is named Charlotte. Yeah, okay, but Charlotte is the important thing. So you can see they're all looking at the spider. So the most important creature in the book is the spider, the little spider making a web. And the story of the book is that this pig, not kosher, I know, but it's the Christmas pig. So he's so happy. They say, you're a wonderful pig, you're the Christmas pig, I'm the Christmas pig. They don't realize they're going to cook him and eat him at Christmas.
No, he's the runt.
Yeah, no, but he's the Christmas pig. I just reread it recently. So anyway, so Charlotte begins encoding messages in the web in English, right? So this is a miracle, right? The spider web has English words in it, like some pig, save the pig, all of this kind of stuff. So this is the first time they see the words. You can see there are words in the web. A miracle has happened and a sign has occurred on earth, right on our farm. We have no ordinary pig. And then Mr. and Mrs. Zuckerman says, well, it seems to me you're a little off. It seems to me we have no ordinary spider. And then Mr. Zuckerman says, oh no, it's the pig that's unusual. It says so in the middle of the spider web. Okay, so the point was the spider that was like.
And the weird thing is that the people that grow the pig has a Jewish name.
Zuckerman.
Zuckerman.
Ah. Well, okay, they're Reformed Jews. What can I say? They don't keep kosher. Well, I think actually in the story they sell the pig to somebody else for Christmas. Okay, okay, so the point is that, what is the point? Is that the important thing is the spider in the web, not the pig. Okay, so what the heck am I talking about? So remember, let's go back to the last few lectures. All quantum sensors can be reduced to qubits or entangled qubits. And the thing that I'm trying to sense is some combination of these two phases. That carries, particularly this one, it's the clock, timing information, magnetic field, gravitational field, LIGO, gravitational wave detector. Everything boils down to an interferometer with a qubit. And the Mach-Zehnder interferometer maps onto a spin qubit, so everything is a qubit, and that phase is what I'm after, right? So if I have a means of teleporting this phase information from one place to another, I can use that. And let's see how. Okay, so remember the atomic clock. This is for the people from Weizmann who apparently are all gone. Who here did not attend any of the other lectures except this one? Okay, so this is for you. Okay, so this is how an atomic clock works. I start in the ground state, which is always up in the computer science. I apply a pi over 2 pulse, which in the Mach-Zehnder is a beam splitter. I put it here, and then the qubit begins to rotate around the equator in the block sphere. And this angle phi is equal to omega t, and t is the time I'm trying to measure. And omega for cesium is 103,226,046,046 periods of oscillations per second. The time, the time standard is, the second is defined in terms of integer number of oscillations of the cesium atoms. And so since it does billions of oscillations per second, with the cesium clock I can measure a second to 1/1000th of an accuracy and precision. Okay, but this could be a gravitational field, a magnetic field, a passing gravity wave, or whatever you want. It's all qubits. Okay, so what happens if I have more than one qubit separated? Okay, so here's how the atomic clock works. This is for the three of you who never showed up before. Are you from the Weizmann Institute? You came on the bus?
Yeah.
It was a minivan? Okay. Where is Diane? He sent you and didn't even show up himself. Okay. So here's how the atomic clock works.
He's stuck on the way because there was an accident, so he turned back. It took him too long to come in.
No, the real reason is that you wouldn't share your whiskey anymore with him, and so he doesn't feel like coming. So Diane came to visit last week, and Haggai...
Yesterday, it was yesterday.
But he was also here last week. And Haggai had to go to a meeting, and we found Haggai's bottle of, what kind of whiskey was it?
It was the late Bushmills.
The late Bushville, it's sitting there temptingly on the counter like this next to two. So I said, Barak, I have not seen you in years, let's have a toast.
Let's finish Haggai's bottle.
Yeah, we finished Haggai's bottle of whiskey. So today, yesterday when Barak goes, and he hides it in the cabinet, and I'm looking where the whiskey is. Anyway, you remember there was one lecture that was almost incomprehensible because I was drinking whiskey at Haggai's place. Like that was fun. Anyway, I take the ground state, I put it into the equator, rotates, then I measure it again. If it's up or down, I get different probabilities, and by taking the difference, I can extract the time between the two pulses, and that's how an atomic clock works, okay? But it's all in this phase. This phase, I'm measuring that. The phase is the important thing. And so you make the detection, take the difference of the upper detector, and you get these fringes. So this is 1/1,000,000th of a second, this is 2/1,000,000th of a second, this is 3/1,000,000th of a second. So you can measure it at that level of accuracy. But now, for the three of you, this thing could be, instead of measuring time, it could be measuring a gravitational field. It could be measuring a passing gravity wave. It could be measuring a gravitational field corresponding to a tunnel under the ground.
Magnetic field.
A magnetic field, which could correspond to detecting a submarine. And so all of this is in this. I want this in each of these interferometers. All right. So let's talk about very large arrays. So in Socorro, New Mexico, this is a photo actually, still Shutterstock. I hope they get rid of them. And they have on the order of 20 big telescopes. Each one of these are radio telescopes. They're the size of a house, an American house, so big. All right. And you can see the photons are coming from outer space in the artist's drawing. But the idea is that, so the guys from Weizmann, physicists?
Yep.
Yeah, okay. I'm pointing at you. I don't know. Please describe to the audience what is the Rayleigh diffraction limit. Loud, get up.
So basically it's...
They can't hear you. You have to get up and speak.
No, they can.
John, why are you being difficult?
All right, louder. I can't hear you because I'm deaf. Go.
Yeah. So it's what the limit itself is, or what the criterion is?
The criteria.
So if you have two Gaussian beams, how to differentiate between the two? So if you could find the two peaks, and it's
Right, okay. So, and the criteria for distinguishing the peaks is related to the separation of the peaks in angle and the wavelength, correct? So,
lambda over the n. Yeah.
and then there's some factor of 1.2 something, which is the first root of the J Bessel function or something. Okay. So what this means is that at a given wavelength, this is radio waves, so kilometers, you're limited by the diameter of the telescope, because the diameter of the telescope corresponds to the angular resolution and the wavelength. Now I'm looking at one object, I can't change the wavelength. And I can make the telescope as big as a house, but that's about it. It collapses after that, and I can't make it any bigger. But if I could phase lock all of these telescopes, notice I use the word phase, okay? If I could make the phase of this telescope and this telescope and that telescope all coherently locked together, now instead of one telescope, I have a synthetic telescope this is about 10 meters, okay? So the synthetic telescope has a diameter of like 60, almost 100 kilometers. So I made one telescope into a 100-kilometer telescope. So that gives me an order of magnitude improvement in resolution of stars and things like this from the Rayleigh criterion. Okay? So the critical thing is, how do I share the phases? With a telescope, this is very slow frequency radio waves. So I just record the signal here, the intensity, and I record the signal here, and I have a good clock, and I put them on a 3.5-inch floppy disk.
Send it over the internet.
You send it over. In the old days, they put it on a magnetic tape. They put it on a big magnetic tape.
3.5-inch floppy disk.
The big one.
An 8-inch floppy disk.
No, the ones on the big wheels, okay? And then, if you have a good clock, you know when the signals, you have timestamps on all the signals, you correlate them in time at your leisure at some central station, and then you get a picture of something really cool. Okay, so this is what the Socorro array looks like, okay? And since it's all radio wave, they use the internet or the magnetic tapes to correlate the signals. The problem is, as the wavelength gets shorter and shorter, the clocks have to be better and better and better, and then you reach a point where you can't phase lock them at your leisure. You have to phase lock them real time. So when you hit already 2 centimeters to microns, you can't do it by just recording it. You have to actually lock them together physically. This is how you do this. So this is a scheme. This was on Mount Wilson in California. So the idea, Alice, is here. Telescope 1, optical telescope here. Here comes the incoming light. Approximately, you can think of it as an entangled noon state. 0 photon is going there. We're going to look at 1 photon. This is what we're talking about today. 1 photon goes here, and 0 goes here, or the reverse, but we don't know, so we add them in superposition. Okay, so everybody knows, even the Weizmann Institute knows the two-slit diffraction experiment. When you calculate this, you get the diffraction because the path here is slightly different than the path here, right? So you teach this in Physics 101. Same thing. The incoming photon, there's only one. If it goes this route, it takes a slightly longer path than this one, just like two-slit diffraction. That gives rise to a phase shift, which is the wave number, k, times the displacement in arm. And that measurement then tells you the angle, okay, and that's what I'm looking at, where it's the angle of the star and the angular resolution. So I can lock these two guys together, and then this telescope is a meter, this telescope is a meter. On Mount Wilson, it gets 100-meter separation. So I make a meter telescope into a 100-meter telescope, and I could put more of these guys. But I don't want a 100-meter telescope. I want a kilometer telescope, or a telescope the size of the Earth. How am I going to do that? Okay. Well, the critical thing is that when they lock these together, and they have a adjustable delay line here, they're basically measuring this phase in real time. But over large distances, it becomes very hard to do this, lock this vibration. Especially in California, you have earthquakes, things are shaking. So more than 100 meters, at this is about 1 micron, is impossible. Okay, so let's suppose I'm going to take a back step. This is a planet formation around a star called HL Tauri, I don't know what HL stands for, which is 450 light years from Earth. So this is the star. You see the ring? And there's another ring? These are planets moving around the star, pushing the dust, collecting, sucking in the dust, and making a ring. So bright stuff is dust, black stuff is no dust, the planets are eating the dust. So I can actually resolve individual planets forming in this thing 450 light years away. Now this is around 2 to 3 centimeter wavelength. So the ALMA system is up in a plateau in Chile, and they still use clocks, but very, very accurate clocks, okay? And they can get, and so this is an image at 2 centimeters. But I really want to have 2 millimeters, 2 microns. I want visible wavelengths. ALMA won't work. Okay, what do we do? Also, remember LIGO? We started out with LIGO. LIGO is a big antenna. What it's measuring is a phase difference between these two arms, right? And I have LIGO in Livingston, Washington, LIGO in Louisiana. They're separated by several thousand kilometers. I would like to phase lock them together, but this is 1 point microns. The best I can do so far is 100 meters, not 1,000 kilometers. Why would I want to do that? Because when the LIGO detects the gravity wave, they take this signal, and they take this signal and average it classically. So they get a square root of 2 improvement in signal to noise. It's the shot noise limit from 2 interferometers. And they have a Virgo in Europe, and they can average that one, and they get a factor of square root of 3. But if you phase lock the LIGOs together, then you get something more like this noon state 1 over n improvement in signal to noise. That's one part of it. The other part is that the LIGO arm is 4 kilometers. So it is specifically designed. You remember, for everybody who was not here, I had a beautiful animated picture of black holes spiraling in. So if you look at these black holes spiraling in, they give off gravity waves. It was a big deal. We detected the gravity waves. So the wavelength of the gravity waves from the inspiraling black holes just before they collide is on the order of a few kilometers. Okay? So as everybody knows, if you make an antenna, the antenna should be about the size of the wavelength for optical receiving. So this is perfect for inspiraling black holes. But there's other things we might want to look at. Everybody knows cosmic background radiation. The sky is filled with radiation at 4 degrees Kelvin, electromagnetic radiation that came from the Big Bang. And this,
but isn't the frequency 100 hertz
for what?
For the inspiraling? Then it's a much longer wavelength.
Right before they collide, it's like thousands of hertz. It's much higher.
Okay, then it makes sense.
Yeah, they only see it at the bloop at the very end. So there is also a prediction that just like there are electromagnetic waves following a Planck blackbody spectrum from the Big Bang, there are gravitational waves that also have a blackbody spectrum left over from the Big Bang. And they have a whole range of wavelengths, and some of the dominant ones should be around the diameter of the Earth. So this telescope is the diameter of has a 4 kilometer aperture, so it won't see those. So, but if I could lock 2 of these separated by thousands of kilometers, then I could see a wavelength 1,000 kilometers, which is a completely new ballpark in astronomy. Well, how do I do that? I have to phase lock them. I can't run a laser from LIGO Livingston to LIGO Washington and lock them. This is count the number of oscillations there, Dan. This is you actually don't see any of this. You just see this thing at the end. Okay, so it's on the order of a few kilometers. Okay, so what are we going to do? Well, one idea is that we use we hook the LIGOs, or we hook the telescopes to the quantum internet, okay, which I just described in the first hour. And I take the phase of one LIGO and the phase of the other LIGO, phase 1 and phase 2, Alice and Bob, and I teleport them to a central station and do my interference there. And then I can bring in Virgo from Europe, teleport all 3 in, and then I get my phase locking, but I don't have a direct laser connection. I'm using the teleportation and the free shared entanglement to bring the phases together on the quantum internet and lock those down, and then I get my telescope or my LIGO the size of the Earth. Now this sounds crazy. The Department of Energy just released a multi-million-dollar call for proposals to study doing exactly this kind of stuff. Okay, And so if it's not LIGOs, it's the telescopes. So I have telescopes instead of 20 or 100 kilometers across, I can lock a telescope in Sao Paulo to a telescope in Canada, and then all these other optical telescopes by teleporting the phase information from each telescope to a central station where there I combine them interferometrically on something that looks a lot like a quantum computer, and then I extract the combined phase information. So this is how you would use the internet, the quantum internet, to make a large distributed array of quantum sensors. Okay, so you asked about the G8Zs, right? So there was a paper by Misha Lukin and Junier at NIST where it's a little bit cheating. So they have a bunch of, these are atomic clocks in space, okay? And you have a ground clock, it's a very big one by the artist's conception. And then these guys synchronize to the ground clock, and then they synchronize to each other. And in the scheme of Junier and Misha Lukin, they use G8Z states, okay? And then they get an improvement where 1 over square root of n goes to 1 over n. They get this kind of Heisenberg limited improvement. The problem, the cheat is you have to read through this Nature paper, blah, 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 sounds really good. Only one of the clocks gets the 1 over n improvement. All the other clocks are still at the square root of n. So I originally thought all the clocks get a square root of n improvement, but just one. But that could be the master clock that synchronizes with the ground station, and then you get this Heisenberg limited idea. Okay, so let's recap for the guys on the Weizmann bus. If I have a source of qubits, and I send it through a phase measuring machine, which could be my clock or my magnetometer or my LIGO, and I detect, if I don't do anything smart, I have separate individual qubits not entangled measuring the same phase, well then you run the numbers and the signal to noise, several ways to look at it, you just average these guys uncorrelated and the signal to noise improves like square root of n. The more guys I have, the signal goes up like square root of n. Either from the law of large numbers or other ways to look at this. Okay. But now I can do something else. I could put the source over here as emitting G8Z states or Noon states or something like that. Measuring still the phases are identical. I detect, and then I get square root of n improvement goes to, instead of minimum detectable phase is 1 over square root n, where n is the number of qubits. It becomes 1 over n, and we get this Heisenberg limit. Simba.
So basically, you kind of glossed over it, but I think you said something that to me seems pretty deep. So you say when you take the LIGO detectors and you phase lock them, then you get the same kind of Heisenberg limit you get for quantum measurements and now you get 1 over n instead of 1 over square root of n. So could you say that by analogy you're getting the same sort of effect in the quantum state simply because when you have multiple spins which are set up and you make a measurement, you're inherently using the phase information because the quantum state and all these spins evolve with the same phase.
I don't think I understood the question, but there is a cheat there. I'm assuming the LIGOs are now using Noon states or something like this as opposed to the coherent states. Or they have the squeeze state, which gives you the 1 over. So you get the slightly better than 1 over square root of n from
So
this.
you're not saying that in general if you took like a bunch of...
That's what I'm about to talk about now. Okay, so in general, okay, here, this is how I make the 1 over n state with the G8 sets, right? But and here are my phases, okay? But there's no reason that these guys, so in an atomic clock, I have a source that produces a 4 atom G8 set state. I get the 1 over square root of n is 2, 1 over a factor of 2 improvement in signal to noise, and then I have parity detection over here. So you saw that, right? Last week, I went through this.
You also said that for the telescopes, right? The classical telescopes.
Yeah, again, in most of the cases I've discussed so far, I'm not talking about 1 over n versus 1 over root n. I'm just talking about making the aperture bigger, okay, by teleporting the phase to a central station.
John, could you clarify and maybe follow up to the simplest question? What exactly are you phase locking which goes beyond phase locking coherent states, which is technically difficult but not a quantum problem?
Yeah, so
What states are you actually entangling or
So in the
phase
case of
locking
the
in an
LIGO and the
interesting-
telescopes, I'm entangling coherence.
So you're creating some two-mode squeezing between.
No,
the
not
LIGO
even
and the
squeezing.
Prof?
I got a phase over here from this telescope's classical phase, there's another one over here, and I'm teleporting to a central station. Technically,
Why is that superior to a classical measurement?
because I can't do it over more than 100 meters. And
You
optical.
can in entanglement.
If you have the quantum internet, I can do it over the size of the Earth. So what you're calling a technological problem requires the quantum internet to solve. So you decide if it's technological or fundamental. But this has got everybody really jazzed up about apertures, and we do it in space, and now the aperture is the diameter of the moon's radius around the Earth, and this is the Chinese are talking about this. So that it's just phase locking classical things, but I'm using the teleportation to do it over long distances. That's it. Okay. Now I'm going to talk about entangling over long distances. So I've sort of cheated a little bit. Okay. So one thing I can do is entangle these guys, and then I get this 1 over square root of that improvement, measuring a single phase. Okay. But now let's suppose I have a bunch of different phases, right? Okay. So the telescope here, 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 and here, and here, and here, so forth. They have different phases. So the previous discussion was I teleport the phases, do a coherent thing, and I get a classical improvement in terms of the Rayleigh diffraction. However, there is a multi-parameter estimation that you can do where now instead of having these guys unentangled, I entangle them with each other. Everybody's entangled with everybody else, okay? So how do I do that? I use the quantum internet. So every telescope, let's call them telescopes, phi 1.
This is GHZ.
Yeah, some G8 said something like that.
Maximally connected is GHZ.
Maximally connected state. Okay, so now you get the advantage that I'm doing a multi-parameter estimation. So the source doesn't have this. So in the old scheme, this was all in a clock. Okay, now the source could be, I don't know where, distributed. You send out in G8Z states. These guys are here. You detect back at the ground station, and now in addition to this giant synthetic aperture, which you said is a technical problem, you also beat shot noise. That's the point here. Now this is actually a hard problem because when you talk about multiple parameter estimation, in the clock with the G8Z states, all the phis were the same. Now they're all different. Okay. It's not known what is the optimal state. If the phis are the same, we know it's a noon state or a G8Z state in the absence of noise. Even in the absence of noise, it's not known what I do here. I can do quantum Kramer Rao bound over here and not worry about detectors, but it's unclear what are the optimal states. So we're back to sticking the states on the supercomputer and looking for the ones that optimize. I guess that's it. Okay. We put this, I thought there would be a big thank you or something. I was working on the slides and then the Alta guy showed up and I had to stop working again. But the point is that measuring these different phases, this is called multi-parameter estimation. So we've done, some people have done some experiments, Ian Wamsley on this, where they have a different phase shift. And there's no relationships between these, there are random phases. And the question is, what is the entangled state that you want to use here? So we try all kinds of different combinations. And anyone that beats the shot noise limit, we go, hooray, and we publish, okay? But the idea then is that now these phases are distributed over a network. They could be sensors, they could be telescope. I send multi-partite entangled states, not your grandma's G8Z state. Howell would say his grandma has a nice G8Z state, but it's something different. We don't actually know for different. The state changes depending on the dimension of the problem.
But you want to estimate all the phases or just the sum of all of them?
No, all the phases,
separately.
Separately.
Because it's an imaging problem.
It's an imaging problem, yeah. But if you use this multi-parameter estimation and use entangled states here that aren't necessarily G8Z, I can't even tell you what they are, then you beat the equivalent of the shot noise limit for the multi-parameter estimation problem. So this is actually an active area of research. We have group theorists trying to figure out what are the. Each time you add a different phase, our computer code finds a completely different state. It doesn't look anything like the previous state. So we're now trying to actually try to do a group theory analysis and say, okay, problem is that as I add more and more different phases and more entangled particles, I'm now trying to. It looks like a quantum computer. I'm trying to simulate my quantum computer on my classical laptop to find the optimal state. And I'm doomed to fail because quantum computers are more powerful than classical computers. So I might need a quantum computer to design this thing to get the optimal state in the first place. But again, these guys are now different telescopes.
But can't you make like a compressed sensing assumption about the phases being simple?
This is like just hot off the presses. So we're trying every damn thing we can think of. So currently we're using a genetic algorithm to optimize the state, okay? Depending on, the compressive sensing only does you some good if the phases have some relationship to each other. But we're assuming they're completely unknown and random, no relation. That's the worst case scenario. And so, yeah, we could, if there's some structure, that this is, everyone in the room is interested in this, right? Okay, there's at least as many papers you can write on this as there are for looking at electrocatalysis and graphene.
I knew we'd get there eventually.
Yeah. Get there.
They don't know what I'm talking about. So
not yet.
So I will end with one joke. This is Heisenberg's favorite joke, H. Heisenberg. So yesterday somebody tweeted me this paper, and the title of the paper, it's in nanophysics something or other, is, does any crap that you add to graphene improve the electrocatalysis? Is the title of the paper. And so what is electrocatalysis? I don't exactly know, but you have graphene, you dope it with stuff, and electrocatalysis means it could be used for a battery or a fuel cell or something like this. So the authors say, well, okay, there are like 42 stable elements, so if you put
86, I think.
84. 86,
No,
you haven't read the paper.
I did,
Yeah.
without...
They found noble gases.
and without carbon.
So we have n different possible atoms, everything from hydrogen to uranium, okay? And then they put in hydrogen, it improves the catalysis of graphene. They write a paper. Then they put in helium, it improves the catalysis of graphene. This is fuel cells and the electric economy and blah, blah. Then they put in lithium all the way up to uranium. And then, of course, now you can put in two elements. I can put in uranium and lithium. So when you get to 3 elements, that's at least 1 million papers you could write. And their prediction is no. And so they said, is it true that any crap you put in graphene improves the catalysis? So in their experiment, I kid you not, he was laughing about this all yesterday. They take bird shit and put it into the graphene and measure the improvement in the electrocatalysis. And it is true. And guano, which is bird shit, any crap that you put in graphene improves the electrocatalysis.
It's a definite the Ig Nobel of the year.
Yeah.
It's definite.
That's where they're going for the Ig Nobel Prize. So that's I couldn't get his attention. I sent him the paper and I go, look at the funny title. And he's like, this is hysterical. And he's like calling everybody, telling about the paper. So he's useless yesterday. Any crap. All right, that's it.
Thank you very much.
Any questions?
Done.
Well done.
At some point, you'll have to fill out a structure evaluation, right? So, and remember, my evaluation is directly proportional to the quality of my stand-up comedy routine.
A very general question.
Yes.
What are the biggest gaps, challenges technologically to realize this vision?
The internet.
Yeah.
Well,
the quantum memory or
memory. And all of the elements of the repeaters are in place. We need the repeaters, but everybody does. And people have been putting like $1 million a year into the development of memories. Now it's going to be $1 billion a year. And if we can solve that, there's some things like NV diamonds where you have a defect in a diamond. This actually has a memory on the order of milliseconds, or room temperature. Everything has to be chilled. So this is the key problem. But in the last talk, I decided to go completely bonkers, and I think assume a quantum memory. What is the most exciting thing we can do? I haven't even talked about distributed quantum computers. Those phases could be states from a bunch of distributed quantum computers. Each quantum computer has this exponential speed up. When I'm combining your data into a central quantum computer, so distributed quantum computing, And then you could, quantum cryptography, there's the Echo 91 protocol uses Entanglement. So, if I have lots of entanglement, I could be actually running E91 in the background all the time. Everything is secure. All of the communications back and forth is secure. And so you have a secure network. So that's the future. I say it's 100 years away. So but there's a group, a lady, Stephanie Werner, her group in the Netherlands just demonstrated the 3-node quantum network. So the record before was 2. So it's improving. But this vision or hallucination, this is the Department of Energy says we want to phase lock the LIGOs together and the quantum computers over vast distances. How would we do that? Well, it would look something like this. Please send me a check. Blumberg, what do you want? Thank you. Thank you so much. Thank you. Nice discussion. Kiefer. When I fly back, my flight is at 6 a.m. Saturday, so I leave the hotel